Okay. Thank you for this kind introduction, and also thank you for giving me the honors of closing off the day with my presentation today. As Victoria explained, I work at a brain imaging facility, so we are the MRI core facility at the RWTH Aachen. So my job is mainly to help make MRI research possible in a university hospital. This means I also get to teach a lot, but also get to play with a lot of fancy toys, like some of them we have in the back. And it is my job to kind of figure out how can we implement these the best in the research projects, some that we do ourselves, but also mostly the research projects that the different groups at our university would like to conduct. So today I would like to talk to you not really about the research findings or the results, but mostly about how do we use the equipment and how do we make our setups. So with this comes also a small disclaimer. So I'll talk about some products from HCC, NordicNeuroLabs, also optoacoustics. My department and I myself are not affiliated with any of these. I also would like to consider this mostly a research talk, not a promotion. We just happen to use this equipment. So I would like to talk about 3 different studies shortly. Each of them use different devices to present stimuli in the fMRI environment. The first one which we would like to talk about uses the visual system HD, which you can see in the back. And it's used to present monostopic and stereoscopic images. The study was conducted by a medical doctorate of ours, Merit Mertens. The second study will talk about how we enabled participant-to-participant communication during fMRI measuring in a hyperscanning study. And to conclude, I'll talk about an ongoing project where we conduct EMDR and ego state therapy with a patient undergoing fMRI scanning. So, first up, I will talk about the monoscopic and stereoscopic presentation. So, the goal of the study was to investigate the concept of peripersonal and extrapersonal space. This is a space that refers to the concept of object perception mostly. In space encoding, we can differentiate between peripersonal and extrapersonal space. Peripersonal space is generally referred to as the space which is body adjacent. So reachable objects, this phone, this laptop, this remote, this is all within my peripersonal space. However, this is reachable, this is manipulatable, and from behavioral studies we also know that responses to objects within our peripersonal space are relatively fast. To contrast this, we have the extrapersonal space. The extrapersonal space corresponds to objects beyond our immediate reach, like the fruit, a glass. I can't reach it, I have to move a bit, but even simply having to take a step to reach something already counts as being extrapersonal space. Cognitive processes involved with this mostly relate to long-term planning, general spatial awareness. Behavioral studies have also shown that our responses to these stimuli are generally a bit slower, simply because we process them cognitively in a different way. So, some of these behavioral studies we happen to have conducted ourselves. In this, we presented our participants with a virtual empty table, which looks like this. This table has, as you can maybe see, it's a bit small, a cup placed on it. This object, in this case a coffee cup, was presented to our participants in 2 different locations, close by and far away, and also in 2 sizes. So we have a small cup and a large cup to compensate for this 3D distance effect. Additionally, we presented this cup in 2 orientations, so either the cup was presented upright or it was presented inverted, upside down, and the participant was simply instructed to tell us was the cup upright or upside down using a keyboard button. We presented this to our participants in full virtual reality using the HTC Vive Pro 2. I think it's similar to the one in the back, but I think it's a bit different. We programmed our environment in Unreal Engine 5. Special thanks to Bruno Letau and Bichir Gri, our systems administrator and biomedical engineering student, for programming this for us. And using this, we were able to present relatively realistic looking stimuli. As you can see on the picture, we still prefer having quite basic stimuli without too much distraction. So it's always a trade-off between realism, immersion, and still having this clean research format, which we always like. So we had to transfer this to an MRI setting. So how do we do this? Well, here comes into play NordicNeuroLab with their visual system HD. It's a bit similar. It's our Google system used in an MRI scanner, which was already presented in a previous talk. The advantages of this, in our case, was mostly the ability to present stereoscopic stimuli, so we can generate this three-dimensional effect. And we happen to know from some previews, I think the one currently running there is also running through Unity, if I'm not mistaken. Yeah, so in theory, all we have to do is take our previously programmed task and transfer this to Unity. Aside from the engineers from NNL, I'm not sure whether anyone here has experience working in Unity. Yeah, a little bit. So we did not, unfortunately. It turned out that nobody in our lab had any experience in Unity, so we had to figure out, okay, how can we still get there? So there are some plugins to transfer one thing to the other. There is the option of simply learning it. But in trying to figure out how to transfer this from one software package to another, I started thinking, do we actually need this real VR? Do we really want to mimic it in the same level as we did with our HTC Vive? And then I thought, what really makes for VR? What are the key factors there? So we know that a key trigger for immersion in VR is this correlation to head movement. You can move your head and your visual field will shift with you. Head motion in fMRI, I personally try to avoid it as much as possible, so this factor we didn't really need. So a second factor is this option of having a three-dimensional environment, like this adaptive 3D space, which you can move through, either with a keyboard or actually walking, while interesting, while able to make immersive environments. This was also not really relevant to our task. We don't want the participants to move around. We want them to sit there in front of this table and respond to our coffee cup. So also this was not really applicable. And then I came to the conclusion, we don't want VR, we want three-dimensional stimuli mostly, which feels a bit like VR, but is slightly different. So we went for the kind of simple approach, because standard 3D images would suffice. We simply took our existing Unreal environment and basically ended up making screenshots, one for the left eye, one for the right eye, one for the kind of combined for our monoscopic control conditions. And instead of having a VR environment, we simply use these images to present 3D stimuli to our participants, which works just as well with our goal system. So this means that we have a final design where we have still our cups presented either in the peripersonal or the extrapersonal space. We presented our stimuli monoscopic versus stereoscopic to also see if this factor influenced the processing of our stimuli. We still had the same orientation, upside down versus normal. And we had this size control of large versus small cups. Specifically, this size control is quite interesting. So we noticed in a previous behavioral study that we did not control for size. We simply generated this three-dimensional cup. I've noticed the problem, well, if you have something close by, obviously it is a larger stimuli than far away. Even though cognitively we process them as being the same size because of, well, this 3D effect, visually, pixel-wise, it had a different size, so we were worried whether this would actually influence our data. So we perfectly matched our stimuli so that the large stimulus located in our peripersonal space was pixel size identical to the extrapersonal, the far away stimulus. We also counterbalanced this by having a very large cup nearby, which looks a bit funny, but we just wanted to complete our paradigm. So I won't have to talk about many results, and it's mostly about the technical setup, but we do have some general findings. As you can see, the paper is still in review. I hope it will be accepted within the coming weeks. We had some basic results. First of all, directly comparing stereoscopic versus monoscopic presentation. So to see this effect of this 3D environment, found general activation V5, medial temporal regions, interparietal sulcus, These are kind of expected regions related to a bit space perception, depth, and even some motion perception areas, because this is kind of triggered by this 3D effect. Keen eye might notice that it's in the bottom left that the t-values are not extremely high for this contrast, which kind of makes sense. We didn't present a full VR stimulus, we presented a 3D stimulus. So we found some effects, but the effects were not huge. I think we didn't find an interaction with our task actually. But all in all, we kind of got what we wanted. Mainly interesting was the comparison between the peripersonal and extrapersonal space. So this far away compared to close by. Actually, all the way around. So here we find regions, mostly this dorsal processing stream, which also makes sense because we have this action-oriented processing, we have this graspability, which we find in the peripersonal stimuli, which makes sense because, as I explained, the extrapersonal stimuli we can't really grasp them, we can't reach them or interact with them. When we invert this contrast and actually look at the extrapersonal stimuli compared to the peripersonal, we find opposite. We find more this ventral stream processing. We get a semantic aspect. We get a scene analysis, because you can see the object, you can analyze it, but you can't really interact with it in a meaningful way. And also interesting, so with the size control, I mentioned that we added this control stimulus, where we presented a larger figure at a further away to correct for the size factor. And even in this size matching, so we compare then the extrapersonal space large versus the peripersonal small, so these were pixel-wise identical, and we see that we still find this similar activation pattern, which seems to show that this difference in fMRI results, it's not to blame just on the size of the stimulus, it's really this graspability, this nearby, this distance effect. Okay, that was mostly the visual study. And with that, I would like to move on to the next study. In this study, we investigated communication, well, among other things, communication during fMRI. In this case, using the Optoactive 2 from Optoacoustics. I think we have an alternative from NNL right in the back. So the study itself was a bit larger. Specifically, it was a study where we used wavelet analysis of MRI hyperscanning. So it's a hyperscanning study. We have the luxury of having access to 2 dedicated research MRIs, so we can perform hyperscanning studies where we measure 2 participants simultaneously, and then use different analysis to measure not just neural activation, but interbrain neuronal coherence. So this is the entire study summarized in one picture. So to conduct hyperscanning and neural coherence, we first have to synchronize 2 MRI scanners. It's written here in one sentence. It's surprisingly difficult to do this. Quickly, how did we do this? Synchronizing MRI scanners comes down to 2 different things. First, we have to synchronize the task which the participants perform. Luckily, this is not that difficult. So this concerns this part of the setup. What we did is we take our stimulus PCs, which we have located at every MRI scanner, and on these we run PsychoPy. So these PCs, we generally refer to them as the clients, and we run PsychoPy on them. PsychoPy is this open source stimulus presentation software. The best advantage of this, aside from being free, is that it is Python based. And when something is Python based, it means it's very easy to either modify the scripts themselves or to program something which interacts with this task. In our case, we had to interact with this task by running a server. So our server runs a Python script, and what this server does is it connects to our client PCs, and it receives input, it receives messages. So it receives a message when we connect to the server, when we start the game, when we start a task, and also every time the participant presses a button, when they perform the task, it sends a message to the server. Then if client 1 presses the button, it sends a message, the server will reply, well, thank you for the message, please wait. Then client 2 sends a reply, and only when both clients have sent their message, the server will send a go or a start signal to both computers, and then the computers will continue their task. And because this is done every single trial, we now have 2 tasks which are basically perfectly synchronized with each other. When we have two stimulus PCs which are synchronized, it's quite easy actually to synchronize the MRI scanners after this. So when it comes to MRI scanner synchronization, I happen to know it is possible to trigger the image acquisition at Siemens MRI scanners using a direct trigger. However, this is not that easy to set up, and we prefer something simpler. So, it's actually this connection, so to go from the client PC to the scanner, but to keep everything synchronized. So, what we noticed is that, at least on the Siemens MRI scanners, when we start a MRI measurement, when we start an MRI sequence, we have this option that it waits for user inputs. You have to press continue, or German University, so you press weiter to start the MRI sequence. Usually the operator uses the mouse cursor to click on it. We figured out you can also press enter on your keyboard. This actually makes things a lot easier because we can simply emulate this enter. So what we did is we set up our PsychoPi from our client PCs to send a trigger which would be synchronized simply over parallel port output. This is then fed into a custom-built Arduino module, and this Arduino module would emulate a keyboard response. And this keyboard response is then sent, so it happens to emulate the enter or return button. This we plug in by USB to the scanner PC, and now we have a server which synchronizes the clients, which then send a message to the scanner, and we have two synchronized MRI scanners. So that's one part of the study. And now that we have synchronized tasks and PCs and MRI scanners, we can let the participants perform a simple cooperation task by QE and colleagues. The task is quite straightforward. The participants view a circle on a gray background. And when this circle, after a small interval, will fill itself with a green color. And as soon as the circle color changes, the participants are instructed to press a button. Only the task is not to press as fast as possible. No, the task is to press at the same time as the other participant. Keep in mind, one of our MRI scanners is located at -2 in the basement, the other is in the 3rd floor. They are separated. They have no way of communicating with each other, but somehow they are tasked with trying to synchronize the task. This makes it a cooperation task. Of course, there is also a control condition where only one participant plays the game and another where they do actually compete in trying to press as fast as possible. But these are mostly used as control conditions. And then, in our case, using wavelet transform coherence, we compute inter-brain synchronicity, so this coherence value. And then we see that specifically during cooperation compared to other tasks, we find synchronization, coherence in specific brain regions, most of them related to theory of mind, cooperation regions, obviously. But the results are not the interesting part. Also, actually, the analysis, this wavelet transform coherence, for people who are into FNIRS, it's quite common there. For fMRI, it's, I would say, uncommon is an understatement. I think we're one of the first who actually bother trying this. So interesting, but not the topic for today. I'm mostly interested in how we continued from this. So as I mentioned, the participants in the original task could not communicate with each other. So we asked ourselves the question, what if they could? What if we let the participants talk with each other? So how do we do this? In our case, the optoacoustics, Optoactive 2, it's noise cancelling headphones combined with a noise cancelling microphone. The regular use of these devices is to either improve operator-patient communication, either between measurements or because of the noise cancelling during measurements, or to present auditory stimuli to the participants. We, however, use it for participant-to-participant communication. So the participants located in different MRI scanners could communicate with each other during the measurement. How we did this was with something, again, quite basic. Mumble, in our case, it's a voice-over-IP chat application. Again, we like free and open source software. We specifically like Mumble because it comes with a built-in recording option. It's not a great recording option because it's a voice chat program. It has some filtering options. If you want to do advanced voice analysis, it might not be ideal, but in our case, we just wanted to record what the participants said, so that was fine. Most of all, it allows us to host a local server within the hospital, which made our ethics committee very happy, since transferring the communication outside the hospital was ethically questionable. So, for our setup, we took our microphone, our fMRI, and this was sent to the stimulus PC, simply USB connection, and the stimulus PC audio was fed to the participant. And because we do that on both scanners, it's no different than when you're chatting with one of your colleagues through Zoom, Microsoft Teams. In this case, the participants just happen to use Mumble, and they happen to be undergoing MRI scanning. And additionally, because Mumble, as you can see in the top left, there's a nice small red microphone, which is pressed. This is a button to mute the audio, as every program has. But it also has the ability to set a keybind for this. And because our stimulus PC runs PsychoPy, we can run a custom Python code to emulate this key press also, so that the task can itself mute and unmute the participant whenever needed. So we have a task-controlled communication between our participants. I'm running a bit of time, so I'll hurry up a bit. So this also allows us to recognize and to record and then transcribe the communication. This transcription allows us to cluster our participants based on their communication styles. In general, we found 3 clusters. So we found people who were mostly silent. We found participants who were mostly chit-chatting. This means non-task relevant communication, like, what are you having for lunch? They actually said this. And finally, we had one group of actually participants who mostly communicated strategically. So this is task-relevant communication. Ironically, the strategic communication group is the one who performed the worst in all trials. This we are still trying to figure out how this is actually possible. I think it's mostly related to miscommunication, misunderstanding between people. So it turns out that just because you're trying to communicate doesn't mean you're effectively communicating. Unfortunately, this grouping did not have an interaction with our task on the neuronal coherence. We think this is sample size related. So we had in total 60 participants, so 30 pairs, split over 3 groups, unbalanced, and unfortunately you don't have that many participants left per group. But I think all in all, the audio introduction in this task was rather successful. Then finally, we have an ongoing study. This is in collaboration with the psychiatry department. In this project, we investigate EMDR, so eye movement desensitization and reprocessing, and ego state therapy during fMRI. So EMDR and EST, these are different approaches on therapy approaches of dealing with traumatic experiences, traumatic memories, in some cases PTSD, but also traumatic experiences in general. Ego state therapy is not that common. So very shortly described by a non-therapist, it basically assumes that our mind, our cognition, we are made up of different sorts of parts of personalities described as ego states, and that the balance between these ego states has been somehow disrupted because of the traumatic experience. And well-trained therapists can try to access these different ego states through communication and either communicate with them directly or even have the ego states try to communicate with each other to try and resolve internal conflicts. That is the best how I can describe it. EMDR is a bit more well known. The idea here is to reactivate this negative traumatic experience, to activate this memory, and then attempt to reprocess this while undergoing this bilateral eye movement. The exact mechanism of why this works is actually still a bit on investigation. The leading hypothesis seems to be at this point that this bilateral engagement, because of the eye movement, it limits the available working capacity. It produces a workload on the brain, which somehow seems to affect the reprocessing of this traumatic memory. So the then question is, why would we do this specifically inside the MRI scanner? So very simple comparison. So we can do the therapy out of the scanner and measure the participant before and after. Then we get, well, 2 measurements, before the therapy session, after the therapy session. And because we're not doing anything specific, you're basically limited to resting state MRI. Definitely interesting, but also quite limited. However, by conducting the therapy inside the scanner, we gain a few extra options. So, of course, we can measure the participant directly before they undergo the session, with the added benefit of having less time between. Because, of course, if you do a therapy session outside the scanner and then prepare the participant for a measurement, time goes over that again. Then one of the steps in these therapies, especially with EMDR, is this trauma recollection. Because the participant is located in the scanner, we can perform a measurement directly after this step. And then even during the therapy session, we can also perform several measurements. In our case, we did during the session 4 measurements in 7-minute intervals. And finally, after the therapy session is completed, we have 1 measurement, in this case then also resting state, afterwards again. So, how did we achieve this for the technical setup? So, for the visual part, it is important for us that we achieve a certain level of patient immersion, that they feel like they're actually communicating with the therapist. So, what we did is we positioned our webcam in the control room to record the therapist performing the session. And the participant viewed through the visual system HD, they viewed the therapist. In this case, they only viewed monoscopic. We only had 1 webcam, so we could not reproduce a 3D image of the therapist, but that's fine. We use some other benefits of these visual systems. Namely, it has a relatively large field of view. If the participant were to look through a mirror, we have this small field of view. Using a goggle system, this greatly is increased. And of course, because the goggle system is pressed directly onto your eyes, there's no distraction from the surroundings, so the participant can feel immersed with the therapist. Additionally, we can provide some visual feedback, not to the therapist, not to the participant, but to the therapist. Unfortunately, we don't have any face cameras available to record the entire face of the participant, nor would this be very effective when you're wearing a goggle system. What we did have was an eye camera. So we did not perform any advanced eye tracking, but we simply verified the eye movement, especially during the EMDR treatment, by giving a live feed of the participant's eye to the therapist performing the therapy. That was the visual part, and then we move on to the auditory setup. So we have kind of 3 parts. We have the patient, we have the therapist, and we have a combination. So the patient wears the optoacoustics headphones, which I described before, which receives the audio from the stimulus PC. They also wear the microphone to be able to talk with the therapist during the measurement. The therapist in turn wears a simple USB headset connected to this secondary stimulus PC. The user headset, so the noise cancelling headphones, they have a push-to-talk button, similar to the standard ones which you have with any MRI system. However, you can imagine performing an entire therapy session constantly pressing the push-to-talk button can be a bit tiring, so you just use a simple headset. And this also comes with an increase in patient privacy. So because the therapist wears a headset, the MRI operator is not able to hear the patient speak. They are also informed of this in advance so that he can speak freely. Of course, we can hear the therapist speak, but it's still a lot different than hearing the patient speak undergoing a traumatic recollection. So, how can the participant and the therapist communicate with each other? Exactly the same as in our hyperscanning study, we run Mumble using this locally hosted server, again, especially with patient communication, happy ethics department. And now the therapist and the patient can communicate freely. And again, because of our hotkeys, we can mute the participant and the therapist in between whenever we want to start a new measurement or have a short break. We can always mute them, which makes the entire process relatively straightforward to run once you get a bit familiar with the operating procedure. And finally, we could even also record the entire conversation. So we wanted to record more than just audio. We used, in our case, OBS Studio. It's a screen and audio recording software, again, open source. So we have to set up our recording environment. Looks a bit like this. So we have to specify what we want to record. In our case, that's 1, the therapist's voice, 2, the patient voice, 3, the camera feed, which the patient sees, and finally this eye tracking feed. So we have all relevant sources, we can record them and then transcribe and even include them in the analysis later. And that concludes my description of the third study. So then finally, a quick shout out to our entire team, the brain imaging facility. And finally, also a special thank you to all the students who helped make this hyperscanning study possible. One of the most difficult parts about performing hyperscanning, in addition to needing access to 2 MRI scanners, is having the staff to conduct 2 measurements at the same time. It's quite a workload, so it would not be possible without all these students. If any of you ever find a CV of any of them on your desk, you should definitely hire them. They're great students. And finally, thank you for your attention. Any questions?
Thank you. Wow, that's quite a setup you have. If there's any very quick question now, we could take one, and then I think we'll need to probably conclude. Margot.
Hey, thank you very much for the presentation. Maybe a big technical question, but did you think about a network communication between your 2 MRI setups with the MRI to communicate?
We considered it. We weren't really sure how to set it up. So we know, as I mentioned, we know that we can trigger the scanner synchronization through, I think, BNC cable, actually. But then it relies on the trigger of one scanner to start the other. I'm not sure how it works with the network communication between the scanners directly. So at the moment, we just, as I mentioned, we synchronize the computers located next to the MRI to achieve a proxy of this.
Send triggers directly to the other one.
Also, so actually, yes. The thing is with any communication, it's usually a bit easier to have one central server which handles this communication. So you can actually use one client PC as the server and one as a client. But we figured that I was worried that this would make an imbalance, because then the server would kind of be faster. Turns out it really didn't matter, but we figured we have a PC which we can use as a server, so we just locally host this, and then we can run them independently. And this also allows us to do quick pilots behaviorally, because we can connect to the same server using any other PCs.